Welcome back to another topic. Today we are going to see about the notation system which we follow to describe the point groups. This is just like a shortened language for the geometry. In general, we follow two different standards to describe the point groups. One is Sheeran-Files notation, which the chemists and physics people use widely, whereas the other one is called HMS system, where then popular that name of that HMS is nothing but it is a Hermann and Mauguin symbol, which is two different crystallographers used or invented these notations. This popularly used among a crystallographer and mineralogist. This particular symmetry element present on the primary directions. We will discuss more on this particular HMS system in this video. So the point group is set of geometrical symmetry operations. Already we saw in the other video that there are different symmetry operations like rotation, reflection, and inversion, in which any one of the point is invariant. That means maybe the axis is unmoved, or the plane or the point which is unmoved during the operation. So, and also we saw these point groups are basically non-translational symmetry. Non-translational symmetry means it not explained with the help of glade plane and the screw axis. And these point groups are basically explains about the macroscopic nature, that means external shape of the crystal. And we know it is a 32 crystallographic point groups which represent the 32 crystal classes. And also we know each class is separated into 7 different crystal systems. The primary difference between this point group and space group lies in two different manner. One is the scale of symmetry. In point groups we talk about the external shape of the crystal, whereas the space group we discuss about the internal 3D arrangement of lattice. And the point groups is a non-translation symmetry operation, whereas the space group includes a translation symmetry such as glade plane and the screw axis. So these are the major difference between the point group and space group. In HMS system, the primary types of symmetry operations are as follows. Is basically it is having 5 different one we can say it is identity. It means the object. The object is called identity, and it has the proper rotation axis. How many fold of symmetry we get during 360-degree rotations, and the reflections. We will understand about the reflections, how the mirror planes are present, how many mirror planes are present, what is the relationship of this mirror plane to the rotation axis. That's what we are going to discuss more with the examples in this HMS. And the inversion is nothing but it's from center of the point. It's a whether in the both the side, whether have the same objects have the same faces or not. Okay, and improper rotation, this is another one which is composed of two different operations. One is rotation followed by the reflection in a plane perpendicular to the rotation axis. And these are the general process which we follow to describe or to find a point groups. First one is to identify the highest order of rotation. Okay, that is also it's a defining symmetry of the particular crystal system. The second one which we have to see is whether there is any mirror plane is present or not, and that particular mirror plane and its relation to the rotation axis also to be identified. Okay, then the fourth one is distinguish the roto-inversion axis from the other rotation axis, and simplify this all these symmetry elements into some notation. That is nothing but it is making a point groups, final point groups. So here we are going to see with a few examples. First we go with this rhomboidal tripyramidal class. Here you can see this particular crystal morphology. From that you can see this from basically from orthorhombic system, and you can see a set of faces. This is the one set of faces, and we have another set of faces at the B axis and similarly for C axis. So when we rotate along this principal axis, like this A axis or B axis or the C axis, we'll get the twofold symmetry. So we'll have three twofold symmetry, and also you can see that's what it is written here. It's a 2 2 2. Okay, then we can also see the plane of symmetry, like one passes perpendicular to A axis, similarly the other one perpendicular to perpendicular to B axis, and similarly for perpendicular to C axis. So these three mirror planes. So here we can say 2 2 2. That means three principal axes have twofold symmetry and also have three mirror plane perpendicular to this axis. Hence the perpendicularity we have to check the relationship between the rotation and the plane of symmetry. Hence by seeing this 2m, we have to see the relationship between this mirror plane to the rotation axis. But all these mirror planes are perpendicular to this twofold symmetry. Hence it is written 2 by m, 2 by m, and 2 by m. We have to verify this through some another evidences. See, just write down all the symmetry elements of this particular class. For example, rhomboidal tripyramidal class have three twofold rotation axis, three mirror plane, and center of symmetry. So here we have described all these symmetry elements through this symbol 2m, 2m, and 2m. This is what it is explained in point groups. Okay, it's a simple notation by which explained all the symmetry operation of the particular crystal system. We'll go with the second example. This is now we'll go with the Rhombic-pyramidal class. Here you can see we have only one twofold symmetry because this particular face not allow to have other twofold symmetry or fourfold symmetry along the other principal axis. Only at the C axis we have twofold symmetry, and so it is written one twofold symmetry. You can see here only one twofold symmetry, and also we have two mirror planes, one perpendicular to A axis and one perpendicular to B axis. We don't have any perpendicular to C axis because this particular face not allow us to have the mirror plane perpendicular to C axis. So the total symmetry elements here is only one twofold symmetry and two mirror planes. Okay, so we have to find the next one whether this mirror plane have any relation with the rotation axis. That means whether it is a parallel or perpendicular. Here perpendicular to this fold axis, twofold axis, we don't have any mirror plane. Unlike in the previous example, all the mirror planes are perpendicular to the two-fold axis, but here it is not present. Hence, this will be written simply as 2mm only, but in conventionally we write mm2 because this particular two-fold symmetry is along the c-axis. Hence, it is written as mm2. Let's verify this with just you have to write all the symmetry elements of this particular class. Once if you verify everything with what kind of symmetry symbol, that means the point group symbol is present. So simply in this manner you can verify with whether it is satisfy all the symmetry elements of this particular class with this particular point groups. So here only one two-fold symmetry that is present in the c-axis and two vertical mirror plane that is perpendicular to A and B. So in this manner it's also there is no center of symmetry. You can see why there is no center of symmetry. This particular face, this pyramidal face, not helps to have center of symmetry in this. So it is simply we can write mm2. So next example we'll see with another crystal model, that is a tri-tetrahedral tripyramidal class. Okay, this is from the tetragonal system. Here you can see this particular model have one four-fold symmetry and four two-fold symmetry. You can see one perpendicular to B axis, another one is perpendicular to A axis, and similarly you can see diagonally from edge to edge there are two set of planes are present. So hence we have to write 4 2 2. Here you can ask there are 1 2 3 4 total 4 set of two-fold symmetry is there, but we have written only 2 times. Actually this is a 4 2 2 2 2, but these two where the A axis and B axis are passing through the similar set of faces, so we have to take only one unique faces, that means only identical faces we have to take. Similarly this two which is passing through this edges to edges, which is unique. Hence it is 4 2 2, and we have to find whether this have mirror plane perpendicular to that or not, whether it is a parallel or perpendicular. Here you can very well you can see this four-fold axis have the perpendicular mirror plane. Similarly this two-fold symmetry which is passing through these faces also have the set of mirror planes, and also this two-fold axis which passing through from edge to edge also have set of mirror plane perpendicular to that. Hence this symbol become 4 by m, 2 by m and 2 by m. Here again you can see there are set of mirror planes. How many mirror planes are there? Accordingly we could able to classify whether it is a uniqueness is there or not. So we can verify this with this particular one. Though we have 5 mirror plane, that means one perpendicular to C axis and one perpendicular to B axis, another one is perpendicular to A axis. So this is the 3 different set. Similarly the diagonal axis also you can see. So total we have 5 different mirror plane, but uniqueness is, if you see, only 3 sets are unique. One perpendicular to C, one is parallel to the faces, and one along the diagonal axis. So the uniqueness is only 3 set of mirror planes are present. We can represent in point groups. Though it is having 5, but uniqueness is there only for 3. And the relationship between the mirror plane and the rotation axis or perpendicularity is there. Hence 4 by m, 2 by m and 2 by m is given for this particular tetrahedral tripyramidal class. We'll go with the last example. Here is a hexoctahedral crystal class. This is from the cubic system. Here you can see, first we have to identify how many rotation of axes are present. Then second one, we have to see how many uniqueness is there in that particular axis. Then we have to understand how many plane of symmetry is there and what is the relationship between this rotation axis and center of rotation axis and the plane of symmetry. So the perpendicularity is there or not. Then we have to check with the center of symmetry is present or not. Here if we go with this 3x of 4-4 symmetry, that is crosses 4-4 symmetry means it passes through this principal axis like A, B, C, and 6 axis of 2-4 symmetry which is passes through these edges, and similarly 4 axis of 3-4 symmetry which is passing through from this solid angle to solid angle. You can see this solid angle to this solid angle. So 4 such axes. We also know this is the defining symmetry for cube. Similarly, you can see 9 mirror planes are present, which is a 3 principal axis and 6 diagonal axis, and center of symmetry is there. Hence, this 4 by m is a unique. One of the uniqueness, and the 3-4 symmetry is another uniqueness which is passing through the solid angle. Similarly 2-4 symmetry also uniqueness because it's passing through the edges. So we have to write 4, 3 and 2. These are the 3 different unique set of symmetries present in the this particular class. Okay, and the relationship we have to find center of symmetry is present or not. So 4-fold axes are the principal plane of symmetry. This one, for example, it is perpendicular to C, and this one is perpendicular to B, and this one is perpendicular to A. So this A axis and these are the 3 principal axes have perpendicular to 4-fold symmetry. Similarly, the 2-fold symmetry which is passing through the edges also have the mirror plane perpendicular to that. Hence it's a 4 by m and 2 by m. And if you see the center of symmetry across this 3-4 symmetry, you will get, hence it's written 3 bar, 4 by m, 3 bar and 2 by m. So here we can find in the point groups as 4 by m, 3 bar, 2 by m. So here as explained earlier, same thing, we have to check all the rotation axis, and then we have to find the mirror planes, and we have to find the relationship between this mirror plane and to the rotation axis. So in this way we could able to find the point groups for any crystal class. So basically we are trying to find first the rotation axis, whether it is a 2-fold, 3-4, 3-fold or 4-fold or 6-fold symmetry, and we are trying to find the mirror planes which is represented by m, and lastly we are trying to find the perpendicularity, that means whether it is a parallel or perpendicular. If it is a perpendicular, then we will write the fold of symmetry like 2-fold symmetry divided by m. That means 2 by m is represented the 2-fold axis, perpendicular to that we have the mirror plane. So in this way it is very simple to understand the point groups of the different crystal system of the 7 crystal systems. And the utility of these point groups is to allow the scientists to predict and explain the fundamental physical and chemical properties. There are certain point groups have special character of that particular nature, we will discuss in the coming lectures. And there are few things I like to highlight here, that the directional variations in the material property are depends on these point groups, such as birefringence, which is represent the optical anisotropic, or piezoelectricity, ability to generate a electrical charge under stress conditions. So there are certain point groups which is have possess this piezoelectricity. Similarly, the pyroelectricities are controlled by these point groups. So in this manner, the physical and chemical property of these minerals we could able to evaluate through these point groups. So that is a major importance, and simple notations we give to understand better the different symmetry elements in the crystal system.